Okay, well, hello everyone. Welcome to the 9th and final Oasis of this term. We're very pleased to welcome Lucien Hardy, who's here for quite a few months, visiting our group. And I'm pretty prepared in any amusing anecdotes about you, so
That's a pretty good thing.
I guess we should get stuck in.
So thank you very much. So this is appropriate that I give this talk here because this marks me joining the quantum pictorial. Have you said that pictorialism? It's a revolution that's been initiated by people in this group. I mean, in some respects, what I'm going to talk about is very much a continuation of work I've done before. So for those of you familiar with it, it's really putting the causal formalism into a context where you have definite causal structure. But the pictures also turn out to be very useful, as I guess you know. This is the talk. There's 5 parts, I suppose. The prelude is just to sort of say something about the motivation for this talk, something I call formalism-locality, and that comes from quantum gravity. And then I'll talk about operational descriptions of experiments. I'll talk about probabilities and the thing we're trying to achieve in this framework. Then I'll talk about the tango, the simple tango, the advanced tango, and also in honor again of the Oxford group here, the teleportation tango. So this is the prelude. I hope you can see that diagram. So this is, formalism locality is, I think, what I want to call a desirable, just remembering Jamie told me to start here. Okay, this formalism locality is a desirable property of the formulation of a physical theory. So formulation of physical theory is said to be, said to have the property of formalism locality if we can do calculations pertaining to any region of space-time employing only mathematical objects associated with that region. So here, for example, we have a region of space-time here. Imagine we want to do a calculation of some probability, for example, pertaining to this region of space-time. Then, if the theory is to have a formalism-local formulation, we should only employ mathematical objects that pertain to this region. In the case of a circuit, it's the same thing, but now we should only employ mathematical objects that pertain to the part of the circuit that we're interested in. Most formulations are not like this. So for example, usually you may have some evolution picture, so you start with preparation at the initial time, and then you evolve the state forward. So if you were interested in this region that I've shown here, you would have to evolve the state forward to cover enough of this region that you can make predictions pertaining to that. But then you would have to include bits outside the given region, because when you evolve the state forward, you basically generate a square box from the initial time to the final time. And so you wouldn't have formalism locality. If there are questions, just interrupt the question.
So why is that something that is motivated by quantum gravity in particular rather than physics?
So it's a good question. So in quantum gravity, I imagine, we want to have definite causal structure. So that means that there won't be a way to pick out special types of shapes, like squares. And so consequently, we'll have to just look at whatever region we're given, however it's specified, and make statements about that. We won't be able to pick out some kind of square which is defined by definite causal structure and say that's the appropriate region to consider this more specialized region with respect to.
But in what sense will one have well-defined regions if there isn't a definite causal structure?
So I'm imagining that operational, at least, you'll be able to talk about the sort of the data that's relevant to some operationally defined region, even if you can't say that the different parts of this region are somehow causally related in one way or another.
Right, because that already seems to have some information about causality.
But I still think it's conceivable that if you have, so basically a region corresponds to some part of the data that you're collecting. And it's still possible to talk about some parts of the data you're collecting without specifying some causal structure on the different parts. Now, in this particular talk, I'm actually going to assume anyway a definite causal structure. So here I have these lines that indicate a kind of definite causal structure. So this won't be relevant here, but it is relevant for the more general problem of quantum gravity. So I think maybe that's something to come back to in the discussion. So that's the motivation for doing what I'm going to do. Although, if you're not interested in that, you don't have to think about it for the talk. So, for the first part of the talk, I'm going to discuss operational descriptions. So I think the best way to think of what we mean by an operational description is the language used by when experimentalists and theorists talk to each other to talk about some experiment. So the theorist says to the experimentalist, I want you to do this experiment. Blah, 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 you should do this. The experimentalist says, yeah, this is the experiment I did. I put this laser here, I put this box here, and so on. And it's a kind of schematic version of the way they talk to each other. The way I'm going to discuss it, the basic object in an operational description is this thing called an operation. So an operation has various features. Well, first of all, an operation corresponds to one use of an apparatus, and it has these features. So it has inputs and outputs. Here's some inputs here at the bottom of the box, and here's some outputs at the top of the box. So you might imagine there's being systems passing into and coming out of the operation region. Then it has a setting. So I haven't drawn the setting on here, but the setting might be some knob that you adjust. If it was a Stern-Gerlach apparatus, for example, you would adjust the angle that the instrument was oriented at. And then it has an outcome set. Again, I haven't drawn the outcomes here. You can imagine that this has an outcome, and then associated with a given operation, there's a set of outcomes. And then if the actual outcome that we see is in the set that's associated with the operation, then we can say the operation A has happened. So this really means that an operation kind of belongs to a family of operations having different outcome sets for the same apparatus.
So what is XA?
So XA is the outcome.
So some particular outcome.
So it could be a light flashes green or red or blue. Those are different. That's a particular outcome. And for a particular operation, it belongs to an outcome set, which may be less than all the possible outcomes. So this may be a subset of all the possible outcomes. So clear?
Why can't the settings and outcome sets be incorporated into the inputs and outputs?
Well, you could imagine going in that direction. I don't want to. So I want these could be quantum systems. You could imagine having a classical system, which is your input and output. Yeah, I choose not to do that.
So given the Stern-Gerlach example which you just mentioned, what would it mean for that to not happen if your XA was not in?
Some operations have only one outcome, which is the operation happened.
Right.
So Stern-Gerlach, if you just think of the unitary, if you just think of that as being a unitary operation, no detectors, then the system passes in, it passes out. There's no outcome. Well, there's just one outcome, which is that outcome. So unitary transformations tend to have that property. We can also use, so this is this is diagrammatic notation operation. This is symbolic notation. So we just number the different inputs and outputs with integers, and then the inputs as subscripts and the outputs as superscripts. It's a very obvious notation. Yeah, so the important thing to bear in mind in all these diagrams is that I've sort of suppressed in the diagram that you actually have an outcome set associated with this. So when you look at a diagram, it's important to remember that that's part of what we mean. Okay. Any more questions? Then we have wires. So wires are things you can imagine systems traveling along. So here's a wire. And we can represent that diagrammatically like this, pretty obvious, or symbolically just by having a repeated index. So here the B4 is repeated. There are some wiring rules. we have at most one wire joining a given input or a given output. We have to type match. I didn't mention it earlier, sorry. Each input can have some particular type associated with it, also each output. So this could be an electron, this could be a photon, for example. So we have to match type. If this is a photon coming out of the output, it has to go into an input associated with a photon. And also we don't allow any closed loops. So it's impossible to go from output to input to output and round to get back to where you started. And that makes sense because remember an operation corresponds to one use of an apparatus. So if you use the same apparatus again, it would appear as a different box in the future.
So how would you model something like recursion when you use an apparatus to say a laser a number of times until something happens?
I mean, either that would be one box over an extended period, or it would be lots of boxes all connected by wires.
But in principle, you don't know how many.
Then I think it's one box in that case. I mean, it's also possible not everything will fit into this model. I mean, I don't claim that all physics will fit into this circuit model we described.
And what's the outcome set for that compound system?
Right. Yeah, so I'll just start on the next slide.
Okay.
So the next thing is called a fragment. So a fragment is just a bunch of operations wired together, like so. And you can have some open inputs and outputs left over. Now associated with a fragment, we have a setting. So that's a setting is given by specifying the choice of knob settings at each of the operations that make up the fragment. And then an outcome set is given by specifying, well, for each operation you have some possible outcome, here and here. And then an outcome set is simply a set of possible outcomes for this fragment in total. So it needn't be a Cartesian product of the different outcome sets for the different operations.
But is there a canonical way of producing an outcome set for a fragment from the outcome sets of its constituent parts?
I mean, if you I don't think there's too much to be gained by thinking about this, because I think this is just a simple sort of mathematics you put on top of the sort of physics structure. If you wanted to keep it simple, we could just always make the outcome sets have only one element. And then it's just a Cartesian product of those. If you want to make it more complicated, I don't think there's a lot to be difficult to make. I mean, for the sake of this talk, we could just demand that the outcome sets for the fragment as a whole is just a Cartesian product of outcome sets here. And since we can always start with the most fine-grained outcome set and coarse-grained later in our calculation, we don't lose anything as far as our calculational abilities are concerned.
I mean, when a wire sort of has both an input and an output in one of these fragments, so they have to agree on which outcome was, I mean, there has to be some consistent view of the...
Each box has an outcome.
Yeah.
Outcomes are different from inputs and outputs.
Right.
So each box has an outcome, and there's no, I mean, they can be, they're just lights flashing on the box. So, you know, we can have green light flashes on this one, blue on this one, red on this one, and what is, you know, blue, there's no, maybe I'm not understanding your question.
So the outcome is not related to the, I mean, so there's no kind of data dependency on the input, between the input and the outcome.
I mean, the outcome set is a specification of an operation. Okay, so here we have B and we have B again, so they both have the same outcome set, because that's two instances of the same operation.
I suppose what I'm saying is in that the lower B and the C, so there's a
Wire, yeah.
there's this wire here, so you'd imagine there was some kind of agreement between the outcome that was observed by B and the input that was observed by C.
I mean, that may be the case, but that would be to do with the physics that describes the
Okay, so
situation.
this is just a syntax, which
Here we just do, yeah. So
getting into that.
yeah, so this is just, yeah, I suppose we put it, this is just the operational description of the experiment without putting any physics in it, without putting any prediction in at this stage. It's just
Right, so I think a computer scientist might say it's the syntax without the semantics, yeah.
okay. That, I mean, I'm not 100% sure I'm comfortable with those terms, but sure that sounds correct. Yeah. So this is oh, and so just we also have, of course, associated with fragments of wiring, which is the particular wiring here. and I'll use the notation SW to indicate both the setting and the wiring. Those are sort of things you condition on for a fragment. And actually, an operation is a special case of fragment, of course. Circuits are also special cases of fragments that have no open inputs or outputs left over. Okay, part 2. The parts of this talk will get progressively longer.
Would it make a difference to think of now you have these things with boxes as inputs and outputs? So it's actually the fact that something is an input is implicit in the denotation, the fact that some things come in and some things go out, right?
Yeah, yeah.
Okay.
Yeah.
So that sort of evokes a bit of carbon structure.
Yeah, yeah, that's right. This talk has, I mean, this is not, this is different from previous work.
Yeah.
Here I have causal structure built into the way we describe
You
it.
could treat this as a graph and then the carbon structure is gone. You just have connections.
You could say that, yeah. I mean, of course, I don't allow closed loops, so the interpretation of this causal structure is natural. But
the arrows are directed in some sense.
yeah, there is definitely there is definitely a direction because these boxes are oriented. I mean, we're only allowed to go from output to input, so you can draw the arrows on, but there's no point because the information is there in the diagram.
Would you saying right at the beginning that the state operation has occurred based on its outcome?
Yes.
So if you drop an operation with no outcomes,
You can have an operation with no outcomes. You can have an operation
Is
where
on the next slide of the circuit, does it not have any outcomes?
but I don't distinguish between. So I'm using outputs is different from outcomes. We go back to this one. So this has inputs and outputs. Those are things which systems pass out of. That's a different word from outcomes. Outcomes are like lights flashing on the box. It's different. Concept.
So that little o of A is nothing to do with DC?
Little o of A. That's right. Yeah, these are different things. Yeah. So these are. You can
So I
imagine.
think that's what confused me earlier.
Right.
Question I asked.
Yeah. So maybe we should get that clear. I mean, I used to draw this with an arrow coming out here, this little arrow indicating that was an outcome. It's like a classical outcome, some data that you record.
Yeah.
And also you can have an arrow indicating a setting.
So
But these are, these could be electrons and protons and things coming into and out of it, which are of a different state.
box B is something that passes through and the outcome is something that happens on the box.
That's right, yeah. So the outcome is light flashes on the box. Yeah. I mean, it's sort of how experiments look. Detectors click, and particles can pass through detectors in principle. So,
Is there any sort of variability in the inputs and outputs? Or are they simply labels to tell you how you can wire things up? Are you just saying...
So for a given operation, you have a fixed input and output.
Okay, so
structure.
you're not distinguishing between different states, say an electron coming in?
Oh, no. So this is just telling you what kind of thing can pass in.
So this is really just a labelling to say how you can patch them together?
Exactly, yeah. Yeah, you can think of these as corresponding to apertures.
So all the variation comes in the settings and the outcomes?
And the way you wire things together.
Okay.
Yeah. And the choice of operations as well. So you can see, there's a lot of variation here. I could choose different operations here. I could wire things together in a different way. And I could also have different, wireless things. Okay. So just a matter of notation. So I'm going to write this, probability of A given B. So A and B are could be some fragments or operations. I've suppressed the subscripts and superscripts just for the moment. We write this as a kind of shorthand notation for this.
Can you read this because I've forgotten about it?
Oh, sorry. Okay. So basically, probability of A given B. So you're going to have that problem all the way through. The probability of A given B is probability that we see an outcome corresponding to operation A, given that we have the wiring associated with operation A, the wiring associated with operation B, and we have the outcome associated with operation B. or this could be fragments.
So you condition on the wiring still.
Yeah. So basically, if you have some experiments where you have some wiring, so you have one part of the. So you're looking at the probability of seeing an outcome associated with the A part. Given that you see an outcome associated with the B part, given all the wiring that you have.
I'm a bit confused by this XA. Are you just saying there is some element in the set of A?
I'm saying. So you do the experiment. You see an outcome, whatever the outcome is.
So you have a, so to speak, a vector of outcomes, one for each box in the circuit. Is that a reasonable?
That's right. Yeah.
way of
Yeah.
thinking
So an
about it?
outcome is
That's your observable kind of data from your run.
yes. So an outcome for a fragment is a specification of an outcome for each box.
So I could just as well have said, so y subscript A, say, is also an element of O of A.
That's right.
So could I write this probability of A given B, could I just replace the x's with y's and it would be a valid expression? Does it matter which element of O A?
I mean, so x is just denoting the actual outcome that you saw.
Okay, but it doesn't appear in the probability of A given B.
Up here. No, it doesn't. Shouldn't. No, it's just sort of like a dummy. Well, let me give an example. Just for preliminary. Imagine, what's the probability that you get a 5 or a 6 when you toss a die? When you throw a dice. Okay, well that's whatever it is. It's a third. So you can toss a dice and you get a 5, or you get a 6. Well, you could write that down like this. Whatever outcome you see should be in the set 5, 6. Okay, given whatever conditions you have. So it's just a kind of coarse graining. Like you actually see only one outcome, but it's, as long as it belongs to the set you're interested in, then you can say that the particular thing happened.
Would it take too long to give an example actually of a circuit rather than the dice? Because I'm really confused now. Sorry.
Okay. Let me use the whiteboard. So imagine this particular apparatus has possible outcomes 1, 2, 3. This one has possible outcomes 1.
So those are the elements of O of that.
No, this is the possible outcomes. It may be that O A is equal to 1, 2. And it may be that O B is equal to 1, 6. Okay. Now I may run the experiment. And of course with the fragment I may have a particular outcome as well. Let's call this fragment F. This is the whole thing. For that fragment I may have a particular outcome which is simply is simply where I see it could be where I see outcome 1 at operation A. Use my notation. This is across. And outcome this is cousin. An outcome whatever 5 operation B. And some other, maybe some more things. Outcome 2, outcome 1. Okay, this is an example where it doesn't factorize.
Right.
So this would be a specification for the fragment. Yeah.
So one of these boxes is not just like an experiment, it's an experiment with a particular set of,
That's right,
subset of outcomes.
That's right, yeah. So the box is not just about what you did, but also about what happened.
But you treat the outcomes as sort of separate from your wiring formalism. Because you could actually imagine that you want to wire them themselves.
Oh yeah, sure. So I take those away intentionally.
They're
They're gone. Yeah, you can imagine those immediately get sent off to somebody. They don't form part of it. You could imagine that. I think if you want to do that, you should just physicalize those things and I don't want to do that. Just.
So do you have a notation for this bigger set? Do you have OA 1, 2, and then there's some other thing which is 1, 2, 3? What is that called?
This is all reference some notation I did in the paper. I forgot what notation I used. Sorry. Yeah. Actually, I mean, in this example here, the natural set for f, it would just be to take the Cartesian product. So let me just do that. I can then say OF is the Cartesian product of OA and OB. We're not going to lose anything by sticking with that. Okay.
So is this OA, is it a set of outcomes that you're interested in rather than the set of all possible outcomes of the box?
Yes, it's set that you're
It's like an event.
Yeah, it's like an event.
The Boolean algebra, however you have
So presumably S of A, there's a whole bunch of different settings you could put on the box in principle, and S of A is a subset of them.
Exactly, yeah. Exactly. The settings, yeah. For the settings, it's not so important. We just pick one.
Okay.
We can even just, yeah. The outcomes are more interesting. Yeah, the outcomes, we pick a subset of possible outcomes associated with it. Yeah, so the notation A indicates all this is being selected in advance. It's part of the description of this operation. So each operation kind of belongs to a family of operations where you have different outcome sets. Because they could have and each fragment likewise. Okay.
So does that sort of imply some kind of selection, as it were? When you do the experiment, you're only choosing an operation means you're only interested in certain.
Oh, but you could, if you do an experiment, you can just consider the set of operations that span, that cover, sorry, all the different outcomes.
Right.
Okay. Because so this diagram is a description of what happened, so to speak. If something different happened, you'd have different outcome sets, and so you'd have different.
When you say what happened, I mean presumably on a particular run, only one thing actually happened.
That's right. Yeah.
Not a set. So there should be a vector of outcomes.
Okay. If you choose to be ignorant of exactly what happened, then
okay.
It doesn't really hurt. It doesn't really hurt what I'm saying. Just to imagine taking the most fine-grained set all the way through. Anyway, I'll try and make the rest of it. Okay. So, first assumption. The probability, prob A, any circuit, so circuit something having no open inputs or outputs, is well conditioned. So what that means is it's determined by the operations and the wiring of that circuit alone, and is independent of settings and outcomes elsewhere. That's my first assumption. The probability that this thing happens should be independent of anything else. Anything else that happens was going on.
But essentially you don't have inputs for A, but you can have outputs for B, I assume.
For D. Well, maybe assumption 1 is still true in that case, but I'm not making that assumption.
Oh, okay. So this is completely closed.
Yeah, it's completely closed.
That's the definition of a circuit, right? Something that is
Okay.
completely closed.
Circuit is when it's closed.
Okay, it's not the whole. Okay.
Yeah. And this is just my assumption. Yeah. What you say may be true as well, but I don't need to assume that.
But what does the word alone then means? Because you're only considering one.
Oh, but you may be in the experiment. You may have an experiment where you're doing. You've got one part of the laboratory where you're doing this, and there's another part of the
You
laboratory.
have a large configuration that may contain a circuit as a part, and then
Exactly.
you're saying that the probability of that part is independent of the rest.
Exactly. Yeah.
Okay.
So it's a very natural assumption. At some level. So given assumption 1, it's very easy to prove that this is true. If I have a circuit, so a circuit can consist of disjoint parts. So here's a circuit, AB, that consists of a part A and a part B. It's very easy to prove that the probability of seeing the outcomes associated with AB is just the product that follows from assumption 1. Just a few lines of algebra. Okay.
So what's the interpretation? You're looking at this is like a space-time diagram of the experiment that you're carrying out. All of these boxes have got outcomes attached to them. You're saying, what is the probability that this experiment happened in this way with these outcomes? But then what's the total space you're working in? What are the other... Because just the fragments themselves, the boxes themselves, I'm not sure how you're supposed to know what else could have happened, which you need to consider in order to know how likely this particular outcome was. I mean, are we supposed to be able to calculate these probabilities based on what you've already told us, or not?
Well, I haven't gotten to the calculation part of the talk at this stage anyway, but so no, I can't calculate them yet. That will come later. So maybe I should show you that form, that calculus, and then you can ask this question. I'm just pointing out that assumption 1 implies this property. It's also a very natural property. Assumption 1 didn't imply it.
In fact, you can even imagine a stronger property, which is that a circuit in any context, in any larger context, I mean, the probability factors is the probability of the context without the circuit and multiplied by the probability of the circuit.
I think this sort of might imply, well, basically, these diagrams are interpreted graphically, so any other thing you put anywhere else,
yes,
you could regard it, if you wanted, as context, or you could regard it as something happening at the same time. If you move these diagrams up and down.
I just mean a larger diagram as this is a sub-diagram.
Yeah.
So if you just taking it out and then multiplying is going to be the same as taking the whole thing together.
Right. Oh, I see. Okay. So maybe one of the other better might do something. Yeah.
When you put it another way, instead of B, you had a fragment. Then, I don't know if fragments themselves get probabilities, but
that'll come later.
Yeah. But anyway, I'm just.
Yeah. Okay. Well, yeah. So we'll see how that works. Okay. So now I'm going to define this p function. So the p function takes as its argument a linear sum with real numbers, which can be negative, alpha, beta, etc., of circuits. Okay. It's just a slightly odd thing because these circuits are just describe things that happen in the laboratory. Still, I can write this down. And it's defined to be equal to the sum of the corresponding probabilities.
What's the sum of two circles?
Well, I don't. Well, all I have to be able to do is write down this. I can write down on a piece of paper this expression. Here it is. I can do that, and then I define this function. And I define this function over such expressions, which here's the definition. I don't have to do anything else. I don't have to answer your question.
You can think of the circuits as the basis of a real vector space.
Sure, but I'm not going to. I'm just going to do this.
It's exactly the same thing.
Is it right? Okay. I guess you could. Okay, so that's the p function. So now I want to define a notion of equivalence with respect to this p function. So I'm going to have different expressions, things like this, actually slightly more general expressions, which I say are equivalent with respect to this function. So let me just give you that definition. So we say an expression 1 is equivalent to an expression 2. So these expressions actually can be slightly more general than the expression I just gave you. It can be a sum of fragments and real numbers. So expression, I'll give you some examples on the next slide. So I'll say that two expressions are equivalent if this is true. And here I've suppressed lots of subscripts and superscripts, so there may be some wiring. So E is another fragment I introduced that may be wired into the expression, the things in this expression. And it has to make the argument in here a linear sum of circuits.
This is what I would call a context, you see.
Oh, okay.
And this is actually, so in computer science, this kind of thing where you define an equivalence through equivalence in closing context is a very important notion. Observation equivalence or contextual equivalence. So it's nice to see this.
Okay, I'd like to know more about that because so I can just. So is that clear what this means? Maybe I should give some examples. So here are some examples of the kinds of things that might be equivalent. So here we have a sum of actually let me look at the second example first. So these are all fragments, and they are fragments which each of them has the property that there exists fragments which can make each of these ones into a circuit. Okay, and then saying that this is equivalent to that is saying that the p function of this expression is equal to the p function of this expression for any fragment that will fit in there. So if this isn't completely clear, don't worry. It'll become clear through use in subsequent slides.
What is an expression like one of those linear sums?
Yeah, but now an expression can be a linear sum not just of circuits but also of fragments.
What's an expression then times E?
An expression that would be. Let's just give a simple example. So here's a alpha. This is a preparation of a system having output 1. Okay. Now I can the kind of fragment I can introduce that will close this would have to be like this, because it has to close into a circuit. And then we can see this is now a linear sum of circuits. Okay.
All the systems have to have the same input and output type.
That's actually, yeah. Simple structure and inputs and
It's going to
outputs.
distribute over.
Yeah. So as long as that's true, so as long as the expression 1 is like this, is equal to expression. And actually, you can also have in here, you can also have an extra, just a constant. Oh no, this doesn't work yet. This has to be the same. You can have a linear. So that's one example. Works. That's the second type of example. The first type of example where you just have a linear sum of circuits. And in that case, E would be another circuit, because the circuit can have disjoint parts. And in that case, you have the possibility of having just a real number by itself in this sum. Okay. I'm not sure I'm going to finish this one. So one example of this, which is true in general. So a circuit is always equivalent to the probability of that circuit. Okay. Let's go. The tango. So we have actually 3 tangos. I didn't have a picture of the teleportation tango. So I'll talk about the simple tango first. First of all, I want to talk about this idea of a fiducial effect. So basically, a fiducial effect is a sort of spanning set of effects. Effects are measurements with specified outcomes. So this picture represents an effect. There's a triangle. The system comes in, and then I actually have a set of them. So here I have, in this horizontal leg, I have a thing coming out which has a label on it. This is the symbol. This is the diagrammatic representation. Here's the symbolic representation of the same thing. This label, a sub 1, goes from 1 up to some value, ka, which is the number of fiducial effects you need. So, what
does the word fiducial mean?
Fiducial is, sort of roughly speaking, it's a set of things used to measure something. So let me show you this. Maybe it makes more sense. So imagine we have a general effect. So this is a general measurement with outcomes specified for a system of type A. So here's a general effect here. Then, in order for this to be a fiducial set, I must be able to write it down as a linear sum of some real numbers. These are real numbers of fiducial effects. Okay, so this is just this kind of thing, where this B sub A1 is a list of real numbers. Okay. And these are the fiducial effects.
Sorry, could you just say again what a fiducial effect is? I mean, in relation to circuits and all that.
Okay, so let me say, for example, in quantum theory. In quantum theory, I can consider making measurements of spin and electron. Okay. Well, and that would be represented by a projector. Okay. Well, I can find a set of projectors that span the space of these projectors, or actually even more generally, positive operators. I can find positive operators. I can find a set of positive operators that span the space of positive operators, so that a linear combination of those positive operators, so that any positive operator can be written as a linear combination of given positive operators. So, imagine I have an arbitrary measurement along some direction. I can write that down as a linear sum with appropriate coefficients of beta. So this set of projection operators span the space of positive operators. So I can write down any positive operator in that way. This is just in quantum theory.
And in terms of what we've been talking about till now?
So here, so in the context of quantum theory, what that implies is that if I had the apparatuses associated with each of these effects, okay, then it would be true that I could write down an arbitrary effect as a linear sum of the apparatus associated with this effect. Because if I take the p function over this, then that works.
So what kind of thing is x?
X, or this triangle box, corresponds to, for example, a projection measurement along the x direction, along the plus x direction.
And in terms of circuits, etc.? Or is it just something different?
No, it's an operation. Oh, sorry, it's an operation.
It's just an operation.
It's an operation. It's an operation having only an input, no outputs.
Okay.
That's one.
How would seeks fit into this?
Oh, a seek would be, if you had a seek would be an example of a fiducial set.
Right. With particularly nice properties.
Exactly. So this is a spanning set of basically a spanning set of effects. If you measure the spanning set, then you can basically simulate mathematically any other effect.
So it's a set of boxes that generate all circuits,
All they generate all effects having equals of that type. Having just one to it. Yeah. So here's a picture. This notation here, where I have a black dot next to a white dot, the symbol A above indicates a sum over this index. It has the same meaning as this equation. And so this is a picture representing that. And it's an equivalence of the sort I was just talking about. Does that make sense? So, I mean, this is really where your basis. This is really just in quantum theory you have a basis of positive operators, and this is just corresponds to such a basis. Just a matter of notation. When I have a black and a white dot next to each other like that, in this context, I can define that just to be like that. Okay. So that link, that horizontal line, just indicates a sum of the appropriate index. What is the white dot? So the significance of the black and white dots will become clear if I use it all. But I'm putting a black dot on the fiducial effects. I want to match black and white dots, so I have a white dot on this box. And this box here, this B box with the white dot on it, this is an example of a duotensor. For preparations, we have the same story. So here's a set of fiducial preparations. And I demand that an arbitrary preparation can be written as a sum over fiducial preparations. Okay. One thing you might notice is that there's always this question, which way does time go? Does time go up or across? So in this talk, time for the operational description goes up, and time for the mathematical description goes across. We'll see resolves that old question. Okay, so this is the simple tango. We start off with a simple circuit. We have some arbitrary preparation for a system of given type. And we have some arbitrary effect for a system of the same type. Now I'm going to replace this box by this. We had previously sum over fiducial preparations. This box by this, sum over fiducial effects. I can get rid of the black and white dots, as a notation, so I have that. Now I'm going to define, let me forget that, just keep the black and white dots in. I'm going to define this object, well I'm going to define this thing here, black and black dot, to be equal to the p function over this object. Okay, so this is basically a list of probabilities associated with fiducial preparations and fiducial effects, because they have different values for these indices. Or I can say this thing is equivalent to this thing. I'm going to call this the hopping metric for reasons I won't have time to.
Wouldn't that differ for different effects and preparations?
Yeah, that's right. Yeah, so the idea is that you should fix a particular set of fiducial effects and a particular set of fiducial preparations. Now you can change them, that's by transforming to a different basis. And just as tensors transform, so the duotensors transform into changes.
Will the metric will also, I mean...
And that will also transform, yeah. Just like it does, just like normally. Okay. So, just an aside on the black and white dots. So I have this preparation box. This is the duotensor associated with the preparation. It has a white dot on it. I can put a black dot on it just by putting the hopping metric next to it and summing over here. And that gives me that notation. Same thing for x. So if I have this, which is what I had on the previous slide here, okay, then using one of these diagrams, it gives me that, or it gives me that one. And then, as a matter of notation, I allow myself to cancel over these black and white dots to have that. It's just a matter of notation. So we have, whenever we have black and white dots, we can cancel them out, or we can reinsert them. So we can insert into the pairs of black and white dots as we like. And we can do that consistently if we have these properties. So we have two white dots is the inverse of two black dots. This is the identity, and this is also the identity. That all works then consistently. So now let me just go through the steps of the simple tango. We start off with a circuit, operational description of the circuit. This is equivalent to this diagram where we've inserted some fiducial elements, which is equivalent to that, where we've taken that and replaced it by the hopping metric. And that is equal to that, just by definition, because we can cancel the black and white dots. So what that means is that the probability associated with this circuit is equal to this. And this is a calculation, this is a sum.
So what is the significance of the little a's and different fonts?
Yeah, so that I didn't. So I use, for operational description, I use sans serif font all the way through. And for the mathematical description, the duotensors, I use just a normal maths font all the way through. Yeah. If I'd had time, there would have been different colours, but... okay. So that's the simple tango. So before I give you the advanced tango, I want to introduce the second assumption. So here's the second assumption. We have an arbitrary operation here, some number of inputs, some arbitrary number of inputs, some arbitrary number of outputs. And assumption 2 says that that's equivalent to this object, which I hope you can see. These vertical lines are a bit faint. Can you see those? Okay. That's equivalent to this object, where this is a sum over a fiducial effect on each of the inputs and a fiducial preparation on each of the outputs. Okay. So that's the assumption. That's true in quantum theory. It's true in quantum theory that you can write this. An arbitrary operation can be written like this. It's also true in classical probabilistic theory. You can do this. So in words, we say that any operation is equivalent to a linear combination of operations, which consists of an effect for each input and a preparation for each output. That's my second assumption. Right. Just a few points here. So in here, I deleted the black and white dots. You can reinsert them. So we have a black dot next to the fiducial element and a white dot next to the duotensor. And so we see that this duotensor here, with all white dots, is what provides the weights over the sum of fiducial elements that I just told you about. Okay. This is an example of a duotensor.
So, could you think of the fiducial effects as sort of a way of changing direction?
I mean, fiducial effects definitely assist going from the physical operational description to the mathematical description.
But they seem to sort of
they assist that conversion in the sort of tango. The reason you're able to go from this picture to this picture is because you have that kind of change of direction.
I mean, do they assist, or are they seem to be the mechanism?
Sure, they're the mechanism, yeah. I wouldn't say that's what they are. What they are is they are a set of preparations or measures. A particular set of preparations. Okay. You look like you have a question. No?
Can't articulate.
Okay. So what are duotensors? So they're like tensors, except that each index is associated with two bases. So you have to choose a fiducial set of preparations and a fiducial set of effects. They transform like tensors, except with respect to two bases. In the paper, it's on the archive, you can see how that works in detail. Here's an example of a duotensor in general. You can have black and white dots on it. And this, in symbolic notation, corresponds to this. So the inputs, always represented by subscripts. The black inputs are on this side, are pre-subscripts, and the white inputs are just subscripts on the other side. Okay. And then for the superscripts, it's similar. Okay. If you have a duotensor like this, you can change the colors of the dots using the Hopin metric and its inverse, like this. So if you had, for example, a duotensor that had all white dots, you can change the dots to be black dots, or whatever you wanted.
Are these two dots the same color, like bell stakes or something?
No. Although, I have more to say about that. Ask for that.
So how should one think of this physically?
I mean, the definition is maybe. So how should one think of what this?
The duotensor.
I mean, it's defined with respect to this property. This physically. Okay. Yeah, it's a list of weights that I need in this sum.
So is it a mathematical artifact, or is it supposed to have some direct physical or operational significance?
I mean, it's if I have an operation and I want to represent the operation with respect to a basis that's specified by giving fiducial elements, then these are the numbers that you get. If I change the basis, I change the numbers in here. That's why the thing transforms. But it transforms with respect to two bases for each leg.
You understand? Black versus white, there's no absolute meaning. It's just.
You could have chosen, you could have inverted them all the way through. Yeah. Okay. So I said this already. If you have all white dots, those are the coefficients in the sum of the fiducials. Interestingly, if I have all black dots, then that corresponds to the probability I would get with this operation if I was to put fiducial elements on the inputs and the outputs. So imagine I take the operation and I put a fiducial preparation in to each input. It's impossible. and I put a fiducial preparation out of each other, then those are the probabilities. Okay. The Advanced Tangle. So we start off with a circuit like this, and now I'm going to insert into these places the thing that results from assumption 2. Okay, do that everywhere. Okay, it's the same diagram, I just stretched it. Okay, so now just remember we have this, which actually implies this. This thing is equivalent to that. So if I take that diagram I had, I can insert white and black dots on each of these links. And then I can insert this into here. Then I get this diagram. So from this I get this. This is equivalent. This one is equivalent to this. Now I take that, and I can cancel over the black and white dots. So I get that. So we'll take the first and the last step. Here is the original circuit, and that's equivalent to a calculation in terms of duotensors. What this means is that the probability associated with that circuit is equal to this. So the striking thing here is that the diagram for the mathematical calculation, this is a mathematical calculation, looks the same as the diagram for the operational description. The only things that disambiguate them are things that I put in place intentionally to disambiguate them, like difference in font and difference in the direction.
And how can you then tell what box is a diagram for a mathematical calculation and what's a diagram?
Well, because these objects, what they stand for is duotensors, which is a bag of numbers. So this is a big sum. This is a big sum. And just like Penrose's notation for tensor calculations.
It's a different font. I mean, that's what's telling us.
Yeah. Well, that, if you want to know, sorry, if you're looking, yeah, it's a different font. If I'd been clever, it would have been a different colour. But yeah, it's a different font, and also it goes in a different direction. For the calculation, the things come out the side of the boxes. For the circuit, they come out the top of the boxes.
What's the significance of the fact that the diagrams look the same?
That's a deep question.
Okay. I mean, could it have arisen that they did not look the same?
Good question, yeah. I mean, great question, yeah.
Counterfactuals in mathematics.
What is nice is that under this very natural assumption 2, they do look the same. And these are very different things. This is a description of something that happens in a laboratory. Okay, this is an experimentalist talking to a theorist saying what he did. This is something that happens on a piece of paper. This is a calculation. And yet, under this natural equivalence, they look the same.
And is this something that we know already, in the sense that we're already familiar with ways of calculating probabilities for outcomes based on a space-time presentation in particular?
Maybe. I mean, it may be sort of taking something we know already, but sort of putting it in more star form. I mean, what I like here, maybe I'll come to that. Yeah, what I like here is this is you don't see here, but in this diagram, this is a hybrid diagram. On this diagram, you have some things that are happening in the laboratory and some things that are happening on a piece of paper. This diagram has boxes and shapes on it that correspond to physics and boxes and shapes that correspond to mathematics. So both things happening on one piece of paper. Teleportation, Tango. Okay, that's nice. This is really just curious. If you take this, that's actually equivalent to the identity. So the identity is equivalent to this thing, which wasn't obvious to me. I didn't put this in the paper, I didn't realize until later. So we can write down, imagine we have an operation which has a random output, okay, and 1/4 of the time, so its effect on the system is to do nothing. Then in addition it has a 4-sided dice, that just gives an output, green sometimes, and our operation is associated with the outcome green. Okay, so that operation could be described as 1/4 I. Just slightly smudging my notation here. We can write that down like this. And now this thing, this bag of numbers, this duotensor, can be split up into 2 bits. When you have 2 duotensors that are separate, they multiply. So this quarter can be taken out, and then we're left with this. So this gives us 1/4 times the identity. This diagram has a mixture of physics, wire corresponds to a system traveling along it, and mathematics, quarter. Okay. So here's the teleportation tango. We have preparation of an entangled state, Bell measurement. This is standard teleportation. I replace each of these as so, using assumption 2. Okay, now this thing here, I can replace it with the hopping metric and then cancel over the black and white dots. So I just get this link. Now, if this is teleportation, then we know that when we do the mathematics and sum over this A and B, as indicated here, this has got to be equal to 1/4 of the identity. Okay, that's a consequence of it being teleportation. We can take the quarter out, as on the previous page, we have this. So we see that this diagram is equivalent to 1/4 times the identity.
So is that knowledge that goes to the quarter, is that something that is sort of coming in from outside, or is it something you can represent within your calculus?
Yeah, so I haven't shown how to do this calculus, and this knowledge comes from outside. I'm just saying it must be the case. If I was to do quantum
does the story extend to where you can actually...
Yeah, not at this stage. Maybe in a future version I can do that. But currently I'm just saying, from our knowledge of quantum theory, we know that this would have to be like this. Well, I should really finish, but let me just go through these last few slides that have pictures in that are fairly self-explanatory. So we can take an arbitrary circuit, we can break it up in whatever way we want into fragments. So here's an example. And then we can do the corresponding thing with the duotensor calculation. So for that same circuit, here's the duotensor calculation, here are the fragments. And then what we can do is we can calculate each fragment separately, and then put them together in a final calculation. So we can do duotensor calculations in whatever arbitrary way we want. We may also be interested in the probabilities for one fragment alone. So maybe I'm only interested in what happens, say, in this fragment in the middle. So given the time I have, I'm just going to tell you that there is a calculus in here that enables you to work out what those probabilities are. Okay, I'm not going to tell you. So actually you have to do a 2-step thing. First of all, you have to see whether it even makes sense to talk about that probability. And there's a calculation for that. And then secondly, if it does make sense to talk about the probability for a fragment, then there's a calculation to tell you what the probability is equal to. And incidentally, I think this 2-step approach is going to be the way that quantum gravity ends up getting formulated, I think. So that's something that appears in my work on the cosloid framework. You can upload physical theories into this framework. What you need is a choice of fiducial effects and preparations for each system type. You need an expression for the fiducial probabilities for each operation, and you need an expression for the hopping metric. So you can upload both classical and quantum theory. This is how quantum theory works. Basically, this is if I have this is a list of probabilities. I can get that from quantum theory in this way. Okay, I won't. This is fairly straightforward, but I don't think I need to go into the details. But you can put quantum theory in this framework. One interesting question is, so normally when we think about physics, we think about things happening in time. Okay, so we have some system, and then we foliate that system so we can tell a story in time, an evolution story. So there's our circuit, and I'm going to foliate it, so I can now think, well, this is my initial preparation, then this is some evolution that happens to the system, then this is some more evolution, and then finally I have a final measurement. Okay, that's the usual kind of story that we like to think about. That foliation corresponds to this duotensor calculation, okay, and I can split that up into 4 duotensors. So this is the initial preparation, this is some evolution, this is some more evolution, this is the final measurement. And what's strange about this is that to do this we have to put in all these identities. So you can see here's an identity, and that's generically the case. If you foliate a circuit, and then turn it into a duotensor calculation, you have to insert lots of identities. I think that's a known fact. We could just drop the identities. So here's the identities. Let's just drop them here. And now all that will plug into, that will correspond to this duotensor calculation here. And this thing cannot be foliated, but it's simpler. So I guess what I'm saying here is that actually foliation is a bad way of looking at this circuit. It introduces complexities. We don't need it. We can do the calculation in this more space-time friendly way without singling out time as a special feature. So foliation can be done, but we don't need it. Summary. We have two worlds. We have the world of physics, operational description. We have the world of mathematics, duotensor calculations. We have these hybrid statements, which allow us to go between the two worlds. You can put quantum and classical probability theory into this framework. Then here's just some general points, like maybe there should be some kind of physics to mathematics correspondence principle. So there should exist a small number of hybrid statements, like assumption 1 and assumption 2, that allow us to translate physical description into mathematical description such that the mathematical description looks the same as the physical description. Maybe that's always possible. Or maybe it should always be possible. Maybe that's a good principle to use when constructing physical theories. Can we make use of these objects? These will be analogous to the cups and caps that you're all familiar with here. Can we go beyond the finite situation? Assumption 2 seems like the kind of thing that we might be able to generalize to infinite dimensional Hilbert spaces, for example. And then finally, quantum gravity, question mark. Every talk should be.
Thompson?
So just to clarify, so it seems that you have, as part of this, I mean, in the duotensor side of it, a diagrammatic notation for at least a sort of convex, sort of linear structure, so additive structure that sort of is going in the sideways thing, which seems but it's sort of compact. I mean, that seems very nice. I mean, but I suppose it relates also to this question: how can one take it to the point where you can actually do calculations within the formalism, as it were?
Within this?
Yeah. I mean, what would it take to do that?
Yeah.
But I mean, is that a sort of reasonable way of putting it?
Yeah. I mean, one could just do it by hand, put quantum theory into this framework by hand,
yes,
and see how it looked, and then you could do calculations. It's not clear that that would be easier than do calculations in the regular framework.
Sure. It would be very interesting if you could absorb at least a large part of the calculations into your just into general diagrammatics of this kind, if there were enough.
Right. Yeah. I mean, so certain aspects would simplify, like this point I made with respect to foliation. So in quantum theory, when you do a calculation, you always effectively have a foliation because you evolve the state in time. And so that's introducing unnecessary complexities. But it may be that you can get rid of that by doing it this way. What we don't have is, at this stage, is a sort of natural, the whole Hilbert space representation is very natural for quantum theory. And it kind of makes calculations kind of effectively more compact than they would be if you just have lists of numbers.
Can you say a bit more about how this helps you as a physicist? So when you're thinking about physical problems, how does the formalism that you present help you out, presumably in the context of quantum gravity?
I mean, this is part of a sort of general program which is aimed towards quantum gravity. And I think one of the problems in quantum gravity is the issue of time. That in physical theories normally you have sort of time, think of a state evolving in time. And in quantum gravity you have some kind of fuzzy causal structure as a consequence of having some kind of quantum superposition over different metrics. Then it's very difficult to think in those terms. So the question is, can we proceed in a different way that doesn't require us to have evolution in time? nevertheless I'm able to do calculations in a way that doesn't require me to evolve state in time. So that's sort of the motivation. That's where it's coming from. The next step would be to make it more general without having the causal structure being definite, and see if we can get towards a framework that's good for quantum gravity.
And you've got some hunches.
Sorry?
You've got some
I
hunches.
mean, I've already done some work like that, but yeah, I have some hunches as to how to take this in that direction. I think it's interesting to start with this start with a clear operational description of your experiment, and then structurally that imposes something on your mathematics. So an experiment in quantum gravity may have certain operational features, or certain operational features being absent actually, the lack of background time, for example. So how can you deal with that in an operational way, and then turn that operational structure into a mathematical framework? So this is kind of a preliminary run of that process, taking an operational description and turning it into a mathematical calculation.
So you have at the back of your mind someone trying to do experiments to probe quantum gravity.
That's right, yeah.
And, okay.
Yes, I imagine. I spent a couple of years working in quantum optical laboratories, and so for me, when I think of an experiment, I'm always thinking of these optical experiments that they did, which is someone in a laboratory with boxes, boxes representing lasers and lenses and things, moving them around and placing them in, aligning them with respect to one another. And I imagine that a quantum gravity experiment might be quite similar to that. You would have some apparatus, perhaps a very big apparatus. You'd have to arrange the apparatus in a certain way, and then run the experiment. And so if you could describe operationally what such experiments look like, then you'd have some of the tools necessary to impose a mathematical structure. Because you saw here very clearly how the operational structure imposed structure on the mathematics.
But you're not bothered about the fact that the causal ordering might not be well defined on your fundamental operations. Your operations, your boxes are at a larger scale than that.
But I am right, but I think I have some ideas about how to deal with it.
Right.
I haven't looked at any detail along these lines at
Right.
this stage. Yeah, I mean, it's a big project. It's a simple problem.
I mean, that's always been your objection in the past to theories which incorporate any causal ordering at any level in their formalism, right? Fundamentally, it might not be a matter of fact that this happens before the thing. In fact, your system might be in a superposition of this happening before this and this happening after this.
Yeah, or something like that. Yeah,
Right.
You've got to be careful. So one of the objections I made to some categorical approaches to quantum theory is that there's a distinction between a tensor product and a composition. And tensor product is essentially putting things next to each other in space, and composition is essentially putting things sequentially in time. Actually, composition is definitely putting things sequentially in time. I mean, Bob has responded to that, but that's my worry, is that if you put that structure in beginning in too fundamental a way.
But why is that not something you've done here?
I have, in fact, yeah.
Right.
But there are certain things that are nice here, so that you can break up fragments into arbitrary ways and do calculations. So here I'm not breaking up a fragment with respect to such a composition and tensor product. I'm breaking it up.
But I mean, of course, in a monoidal set, you also have the ability to break a given thing up in many different ways.
Right.
You have a lot of commutations, and again, you have many different choices of foliation. It's not intrinsic to the.
Would the foliation have to be somehow respecting the interpretation of the space-like foliation?
No, not necessarily at all. Also, in a compact setting,
there are some constraints coming from the monoidal structure. I mean,
because the example I gave, so this is a foliation, and it has certain properties. So I can't get. Here's a foliation. I can't get from here to here without going back along the way.
yes.
Whereas the other breaking up I showed you didn't have that property. It wasn't broken up in such a way. And so So, because the previous work I did insisted on foliation, and it seems to me that sort of comes from the point of view that we're evolving a state in time. And so I wanted to get away from that, just thinking about just breaking up certain arbitrary ways and doing a
I
calculation.
can't see why the sort of possibilities you have here would be different in kind from those you have in a monoidal category.
I mean, in some sense, what we have here is another kind of structure, so it's not as if
So
it's
it's
a bit different, but
no, absolutely.
yeah, I mean, my motivation is perhaps different, but yeah. I mean, have people thought about that in the category approach, breaking those calculations up into arbitrary pieces without respect to some foliation?
Yeah, it's a fundamental part of what that's just built in automatically and used
Yes.
implicitly all the time.
So I mean, again, it's a sort of contextuality property that you can isolate a sub-expression, replace equals by equals, and the whole thing is equal. And so therefore it's implicit in any use of any kind of graphical calculus, where you do a local rewrite in any larger, wherever you can recognize the left-hand side of an equation, you can replace it locally, and the meaning of the whole thing stays
Okay,
the same.
so that could just be some fragment.
Yeah.
You take that.
Isn't that essentially what mathematics
It's what logic tells you.
But the point is, generally, you can also deform these diagrams and without changing what they evaluate
Right.
in ways that don't respect any particular foliation.
Right. Yeah.
That's-
Yeah. Yeah. I mean, you have that as well.
Okay, so any more questions?
So there was an assumption that you introduced to do with the fiducial thingy-bobs that allowed you to go from writing things operationally to mathematically. You said that, I think it was assumption 2, and you said that it doesn't always hold, and that it doesn't hold for real quantum mechanics.
That's right. Yeah.
Which, given the fact that it seems so natural that a sequence of operations is something that you can calculate,
Right.
I didn't understand why.
Why it doesn't hold for real?
Yeah.
I mean, there's a property. So this implies a property called local tomography, which is something that a lot of people use.
Okay.
Yeah. So you can see. So to see that, just consider an operation which has no inputs, such as preparation. Then you just got outputs, and it's pretty straightforward to see that effectively implies local tomography. So this is a stronger assumption. Well, it's not provably. it may be equivalent to local tomography, but at least it could be a stronger assumption of local tomography. And we know that real Hubble spaces are consistent with local tomography. It is consistent with a property called bilocal tomography. And you could imagine generalizing assumption 2.
What's bilocal tomography?
Bilocal, so Bill Wooters and I put a paper out a month ago. Bilocal tomography is the idea that in order to establish the state of a system, you only need to make local measurements and also pairwise measurements on your systems.
Okay.
And it turns out that you don't need to make measurements on triples of systems and higher. And it turns out that real Hubble space is consistent with bilocal tomography. You can imagine generalizing this assumption.
Okay, so if you had a tripartite real Hilbert system, you could work out by making kind of two-party measurements.
Yeah.
Okay, I didn't know that.
Yeah. So,
But, okay. But why is this to do with local tomography? Because there's only one operation and not two. So,
yeah. So let's
why
see.
is there any idea of locality
Sorry,
or?
so there's a simple, succinct statement of this. So we get it. So just imagine an operation which is a preparation. So it only has outputs, no inputs. So we only have this here. Then I can do tomography on that preparation by just putting fiducial elements, fiducial preparations on the ends of each of these.
Okay.
And that's obvious. Yeah, that's obvious.
Okay.
Yes, it is obvious.
Are you agreeing or you just?
Okay.
So how crucial is this to like this symmetry picture? That is this a theorem that you've got this diagram in space, and then you've got sort of this flipped image as the diagram of the calculation.
Right.
That's a theorem. They're exactly the same?
Oh,
Well,
I mean,
up to mirror symmetry.
yeah, it's sort of obvious. Again, and this time it is obvious. If you just look at this Advanced Tango, okay, you follow the steps through, and imagine this for any
And
surface.
this property is key to the
This property is.
of the local topography.
Oh,
Or whatever.
This
this assumption two, which is I call it what do I call it? Operations are fully decomposable.
Yeah.
It's key, yeah.
So that's maybe like the key thing of the whole story here, that
Yeah.
with this assumption, you get this direct translation from the
Yeah.
topology, from the operation topology, the sort of mathematical computation
Yeah.
topology.
Now it may be that you can have weaker assumptions than this that achieve the same thing.
Yeah, it seems kind of on the nose,
Right. Yeah.
if I see well. Right? It's really that what you need to make it work.
Yeah. Yeah. This is exactly what. Yeah. This makes it work at least.
Yeah.
It may be something weaker that make it work as well. But I haven't tried.
So it's a kind of linearity assumption in some way, isn't it?
I suppose. Yeah. Well. Yeah, it's an assumption about. Is it linear? It's an assumption that if you choose to represent an operation as a linear combination of things, then you can do it in this way.
It's
It's a
translation
sort of
correlation.
matricial representation, isn't it?
Yeah. Yeah.
Matrix of correlation. Correlation
Matrix. It's saying you have a correlation matrix.
So,
Yes.
It's like representability as correlation matrices of interactions which take place in space.
Yeah.
I mean, the fact that you get a stronger decomposition property with complex numbers than with reals is just generally mathematically not so surprising. I mean, they're analogous things because you can just solve more equations with complex numbers.
Oh, right. Okay. Yeah.
Shall we thank Lucien again and have more discussion over cookies in the community?